Welcome back, everybody. I'm going to try and get this video done in two. It might be 3 parts because there's just so much to talk about. In the prior video, I talked about the toxic data from previous oligonucleotide trials, and I thought it was important to bring that up. The reason, in part, for bringing that up is I recently watched an interview of a researcher who was working on this trial, and the word the cure came up, the steps towards the cure, and I felt like the interview itself was a little misleading because what they're doing is actually combining two different delivery approaches, which you cannot do. That's two separate trials. The way the therapy affects the body is different in each approach, and when you go in systemically, you're hitting the organs and the liver and the kidneys, and until you know that you can do that in humans, that data shouldn't be brought up. You have to test to make sure it's actually feasible, that it's a safe alternative, because what the mouse data suggests and the primate data is we get different results, way different. Things that are very safe. You can get robust extensions of life in the mouse that we see issues in a non-human primate. Let's not forget that a mouse has 85% of the DNA of a human, and a non-human primate is 98, 99%. So some of the issues that we might see in a primate would probably be a little closer to a human. Even with that, even that close genetics, that 1% is still different, millions of codes of DNA that are different. So I think it's important for families to understand that. I'm going to use tonight the two papers to show you in their own words that an intrathecal approach, the one that we're actually moving forward into a clinical trial with, is not as successful in extending the mouse life. It's successful in upregulating SMN2, but we didn't have a large extension of life. That was in the systemic, which hasn't been proven to be safe yet. So we see great data in the systemic approach with oligonucleotides, right? We're talking about the same product, not two different products, same exact product. We show a great extension of life, but we haven't shown it's safe in a non-human primate or a human. So to say that we're marching towards a cure when we're going in intrathecally, to me, was a little misleading, to say the best. There are issues with an intrathecal approach. There's issues with systemic. Systemic, you could get toxicities in the organs. You have to use a larger dosing. The benefits to an intrathecal approach is that you could use a smaller amount of product. You're not going to have the same toxicities circulating through the organs and through the bloodstream. And it's going to be cheaper for a company to go that route. They produce less product for a treatment, and there's more profit in that. However, with an intrathecal approach, what's shown and what these two oligo papers that I discussed tonight is that in an intrathecal approach, the treatment localizes into the CNS. It doesn't hit peripheral. And I'm going to go into that, but I just wanted everybody, as we're talking about this, I just want everybody to see what an intracerebroventricular, right, a cranial shot looks like, right? It's going back here, right? That's the approach, right? An intrathecal is going into the spinal fluid, right? It's an injection here. And a systemic can go into the veins, right? Or in the mouse model, they go into a facial vein. So they choose with gene therapy, they use a facial vein because the mouse is so small. That's the easiest vein to find. Now, in addition to what happens in the body with these different delivery approaches, you have to think about the delivery approach itself, right? So the data in these papers show that in a stronger mouse model, in a type 3 mouse model, the drug lasts up to 6 months, right? The treatment lasts up to 6 months in a stronger mouse. However, when you look at the weaker mouse model, it only lasts 30 days. So why is that so important? Because if you're talking about an intrathecal approach, you're going to have to penetrate the spinal fluid every month if we're going by the animal data. And if you're going that frequently for these injections, which the patient's going to need for the rest of their lives, aside from the toxicity of the drug itself, there are things that can happen, like spinal meningitis. It's a real possibility, that we have to discuss. I think what hasn't been brought up is if we're going to go this delivery approach for this program and others, that's going to be needed over the course of a lifetime, we have to talk about surgically implanted pumps, right? Which I haven't heard discussed. Is that going to be a separate clinical trial? Who knows? So I wanted to read to parents about the autonomic nervous system. So in the systemic approach, where we see great data, which hasn't proven to be safe in a non-human primate, I haven't seen the studies yet, we see that it rescues autonomic nervous system, and we see that in SCAAV9, the gene therapy. It corrects the autonomic nervous system issue. So how important, right? We've heard CNS, skeletal muscles. How important is the autonomic nervous system for SMA? I want you to be the judge here. The autonomic nervous system is a part of the peripheral nervous system that acts as a control system functioning largely below the level of consciousness and controls visceral functions. The ANS affects heart rate, digestion, respiratory rate, salivation, perspiration, diameter of the pupils, urination, whereas most of its actions are involuntary. Some, such as breathing, work in tandem with the conscious mind, right? So the more effective, the parents with the more affected children, you see these things. You see the heart rate, right? Issues with heart rate, digestion, right? That's why there's talk of a specific diet that's easily digested within the community. Respiratory rate, perspiration, right? Our children's sweaty hands, diameter of the pupils, right? When our children go outside, how they're sensitive to the sunlight. I mean, all of these things point to an autonomic nervous system. But it's not really discussed. And up until recently, a new paper came out to say that we see it in the patient and we see it in the animal. So if you're choosing a therapy that cannot target the autonomic nervous system, how much of a correction can you see in the disease, right? So let's continue. The enteric nervous system is a subdivision of the autonomic nervous system that directly controls the gastrointestinal system in vertebrates. The ENS has been described as the second brain. Vertebrae studies show when the vagus nerve is severed, where it makes a connection to the CNS, the enteric nervous system continues to function. In vertebrates, the enteric nervous system includes efferent neurons, afferent neurons, and interneurons, all of which make the ENS capable of carrying reflexes and acting as an integral center in absence of CNS input. There are more nerve cells, very important, more nerve cells in the enteric nervous system than the entire spinal cord. The sensory neurons report on mechanical and chemical conditions. Through intestinal muscles, the motor neurons control peristalsis and churning of intestinal contents, right? We see this in the more affected kids, right? The constipation. So, I mean, this all points to things that are very important, highly important in SMA. Other neurons control the secretion of enzymes. More than 90% of the body's serotonin lies in the gut, as well as 50% of the body's dopamine. So, I mean, let's discuss what SMA research has entailed, right? It's entailed upregulation of SMN2, try and get it to express more, or putting in a new SMN1 gene completely. And the point of that is to get them inside the motor neurons. So if you have a therapy that's just correcting the skeletal motor neurons, right? And it can't target the motor neurons of the autonomic nervous system. That's a huge part of the disease you're missing. So let's go into the papers themselves. Peripheral SMN restoration is essential for long-term rescue of severe spinal muscular atrophy mouse model. So this is a paper by Adrian Craner, and it says non-central nervous system pathologies, including cardiovascular defects, were recently reported in severe SMA mouse models and patients, reflecting autonomic dysfunction or direct effects in cardiac tissues. Here we compared systemic versus CNS restoration of SMN in severe mouse model. So they're comparing the same product. They're comparing oligos, whether it's intrathecal or a systemic approach. Systemic administration of ASO 1027 to neonates robustly rescued severe SMA mice, much more effectively than intracerebroventricular administration. subcutaneous injections extended the median lifespan by 25-fold. So what they saw in the intrathecal injection was, I believe it was 7 to 9 day extension of life. They had effectively upregulated SMN2, but it didn't translate to a robust extension of life. They only saw that in the systemic administration. These results suggest that the liver is important in SMA pathogenesis, underscoring the importance of SMN in peripheral tissues and demonstrating the efficacy of a promising drug candidate. This is their words, not mine. Delivery of the ASO only in the CNS efficiently corrected SMN exon 7 splicing in the spinal cord and led to a striking increase in SMN protein levels. Right, so right there, it was very efficient. The intrathecal method is what we're going to do in humans, but that it was very efficient in upregulating SMN7, but modestly extended the median survival to 16 days, with a single pup surviving for 1 month. In marked contrast, systemic treatment with 2 SC injections resulted in median survival of 108 days. So when they used the systemic treatment, it was a much larger extension of life. Combining ICV and SC injections of the ASO further increased the median survival to 173 days, and 2 additional SC injections on postnatal day 5 and postnatal day 7 after the initial SC injection at postnatal day 0 and 3 extended the median survival to 137 days. ASO 1027 as an SC injection given twice between postnatal day 0 and postnatal day 3, systemic treatment with ASO resulted in a dose-dependent increase in survival, with the median survival increasing from 10 days to 84, 170, and 248 days, respectively. At the highest dose tested, the ASO given systemically resulted in long-term survival comparable to the best results achieved by adeno-associated virus expression of the SMN protein in slightly less severe mouse model. So they're bringing up gene therapy there. We'll discuss that later. Remarkably, 2 of 14 mice in the SC160 group and 2 of the 18 in the SC80 group are still alive and active after 500 days. So the SC160 group is 160 micrograms per gram of tissue. All right. So in the intrathecal approach, they only used 8.25 micrograms per gram of tissue. So you see, it's like a 20-fold increase, almost 20-fold increase in dosing. We detected a dose-dependent increase in exon 7 inclusion in the spinal cord, brain, liver, heart, kidneys, and skeletal muscles, with the strongest effect occurring in the liver and the weakest in the kidneys. By contrast, ICV administration of the ASO resulted in a much more robust change in exon 7 inclusion in the brain and spinal cord tissues, but had very limited effects in peripheral tissue. So right here again, they say, that this had more effect, the systemic delivery. These data suggest that transiently increasing SMN expression in peripheral tissues during the first few weeks of life has a profound effect on long-term survival of severe SMA mice. So here's another program saying we have to get in early. We have to get in while we can still target motor neurons. However, our data indicate that the SMN restoration in peripheral tissues in combination with partial restoration in the CNS can achieve efficient rescue of severe SMA mouse model. In mice that had been treated systemically with 160 micrograms of ASO 1027 and sacrifice on postnatal day 9, histological examination of tissues or organs associated with SMA revealed striking improvements consistent with the markedly increased survival of mice in the SC160 group. So, that's all I'm going to go through on this paper. I'm trying to cut these videos down. This is my 3rd attempt. Every time it's half an hour. So let's go to the other paper, the Pacini paper, which is the intracerebral ventricular, which was the model for the intrathecal program that's moving forward. Several therapeutic strategies are under development to treat SMA, including gene therapy to replace, here we go, gene therapy, to replace the defective SMN1 gene or small molecule drugs to boost the inclusion of exon 7 during splicing of SMN2 mRNA and so increase SMN protein production. Although these strategies have shown promise in cell lines and animal models of SMA, they have shown little success in treating human patients with the disease. So they said that the drugs that tried to upregulate SMN2 and by replacing SMN1 with gene therapy has shown little success in treating humans. But I mean, we all know that none of these programs have shown success in treating SMA humans. Oligos haven't either. Now, this was on the Antisense. The name of the paper is Antisense Oligonucleotides delivered to the mouse CNS ameliorate symptoms of severe spinal muscular atrophy. This is the Pacini paper, and what I'm reading right now is the editor's summary. The authors calculated that the ideal therapeutic dose for ASO 1027 to ameliorate symptoms of disease was 8.25 grams per gram of tissue, right? So that's another concern right there. Hold on. You see that 8.25 grams right there? They report that the amount of SMN protein produced peaked at day 16 after injection and then waned, disappearing completely by 30 days. This may fit with their observation that many of the treated SMA mice died at 21 days after weaning from breathing difficulties, perhaps due to the loss of SMN protein. So, you know, the reason why I brought up the dosing was because everything's micrograms in the paper, and in the editor's summary, he's saying 8.25 grams per gram of tissue would be needed to ameliorate symptoms. Now, you know, to put things in a perspective, there's 1,000 micrograms in a milligram and 1,000 milligrams in a gram. So they're talking about essentially 8,250,000 micrograms. Testing of such ASOs with 2,O-methyl chemistry showed that multiple injections over time were required to affect SMN levels in vivo. So here they talk about the different tissue concentrations of ASO 1027. Now this is the intracerebroventricular approach. As measured in the cervical region, were highest 8 to 10 micrograms of ASO per gram of tissue at 3 days. These levels declined to 2 micrograms of ASO gram per tissue at 16 days and to 1.5 microgram of ASO tissue at 30 days. Measurements of the levels of full-length SMN2-derived mRNA in the lumbar region showed a 3- and 6-fold increase with ASO 1027 treatment at 3 and 16 days respectively. However, these elevated levels of exon 7 occlusion were not sustained, returning to pre-treatment levels on day 30. So here we go again. You know, I'm talking about how frequent an injection is going to be needed. These are the severe animals that they're showing this data on. To assess whether treatment with ASO 1027 provided a survival benefit, we injected SMA mice at postnatal day 0 with varying doses of the ASO ranging from half to 8 micrograms. Now, intracerebroventricular injection of 16 micrograms or higher resulted in significant death rate within 24 hours of administration, indicating that an 8 microgram intracerebroventricular bolus injection was the maximum tolerated dose in postnatal day 0 mice, right? So they found the lethal dosing. It was 16 micrograms. All of the ASO 1027 treated SMA mice, regardless of dose, were ambulating and well-groomed, which persisted in animals that lived beyond weaning. However, most of the weaned SMA mice were eventually found dead in their cage, indicating acute sudden death. In some instances, weaned SMA mice developed breathing difficulties that included a decreased rate of respiration and shallow breathing. So when the doses were stopped, when the treatment was stopped, they returned to exhibit signs of a typical SMA animal. So here's the primate studies, which they did. A dose of 3 milligrams of ASO 1027 was infused into the intrathecal space 1, 3, 7, or 14 days. Each monkey was killed 5 days after completion of the infusion. There were no deaths or clinical adverse effects observed during the in-life portion of the experiment, indicating the monkeys tolerated the infusion. Yeah, 5 days after they did, you know, and if you see, it's 3 milligrams on the front page in the editor's summary. They were saying that you need 8.25 grams. Histological examination of brain and spinal cord tissue sections stained with hemotoxin and eosin did not reveal overt pathology attributed to the drug, further demonstrating that ASO 1027 was well tolerated. However, a formal toxicology study that extends over a longer investigational period will be needed to be performed to understand the safety profile of ASO 1027. The pharmacological effect of the ASO was not measured because non-human primates lack the SMN2 gene. The inability to sustain elevated levels of SMN protein at 30 days suggests that the ASO tissue concentration at 16 days was not capable of modulating splicing. Hence, the minimal concentration required for efficacy must be greater than 2 to 3 micrograms of ASO per gram of tissue. The loss of SMN protein by 30 days is consistent with the Kaplan-Meier survival curve, showing a median survival of 26 days, right? Untreated mice live 16, so 10-day survival. Intracerebroventricular infusion of ASO 1027 in adult SMA type 3 mice loaded the spinal cord with ASO 10 micrograms per gram of tissue, resulting in greater than 90% of the SMN2 transcripts containing exon 7. However, the ASO tissue concentration of 10 micrograms in the type 3 SMA mouse model was sustained for at least 2 months, and the effect on splicing was maintained for at least 6 months. It is possible that developing and growing neonate may promote the cellular depletion of the ASO more rapidly than in the adult. Regardless, it is reasonable to predict that the pharmacokinetic data in the current neonatal study might be a more relevant indicator of the kinetic profile to be encountered in infants and young children with SMA. So even though it lasted longer in the larger animals, they're saying we should go with the data in the severe mouse model, right? The eventual cause of death in ASO 1027 treated SMA mice is not known. However, the sudden appearance of animals found dead, coupled with the observation of acute breathing abnormalities in end-stage SMA mice, suggests that cardiac and/or respiratory failure may be responsible. Cardiac failure, that is bradycardia, thought to be caused by autonomic dysfunction, right, was recently described in the severe mouse model and in SMA patients. In this scenario, a drop in the ASO tissue concentration in the lower brainstem may lead to the loss of autonomic function in the cardiac system, which would explain the sudden acute appearance of respiratory defects in ASO 1027 treated mice. A similar acute breathing aberration was observed in the long-lived SC AAV8 HSMN treated SMA mice. So they're talking about gene therapy mice, but they're not talking about the AAV9 where we did see the correction, right? They chose a different program. Future studies in large animal models that investigate the optimal metrics for delivery, for example, bolus versus slow infusion, catheter placement and timing and frequency of repeat administration, and safety will be required to determine the feasibility of translating ASO 1027 to the clinic. So there you have it. You know, I'm not tied to any program. We don't have licensing on any of these programs. We're not interested in making money. We do this as volunteers. I'm for whatever program works. So whether it be oligonucleotides, gene therapy, or anything else, that'll be the programs that we're interested in. But I'm breaking down the data here, and I'm showing that I see a lot of comments in the community of, the cure. I mean, this is just an intrathecal approach. We already know it's a 10-day survival in the mouse data, and we've experienced other programs with a 10-day survival. So we kind of have a barometer of what we can expect. So when we do move forward, if we can show oligonucleotides systemically are safe in a non-human primate and move forward with a clinical trial using that delivery approach, to me, I would be a lot more excited about it. There's other compounds. They've made improvements of oligonucleotides. The backbone has changed, the chemistry. There's another program using morpholinos, which has great data, and that's a form of oligonucleotide. So, I just wanted to give you my perspective on the upcoming clinical trial. I'll post the links. You can do the research yourself and see what you think of these programs. All right. Thank you very much for listening.